Right now, trillions of tiny particles are shooting through your body, and almost none of them touch a thing. We call them ghosts. Scientists have found 3 kinds, but a 4th may be hiding, one so shy it feels no force at all. A particle the rules of physics forbid, one that could be dark matter itself. Deep underground and inside the biggest machine ever built, CERN is hunting it. If this thrills you, hit like and subscribe. Steady yourself, the hunt begins. Hold out your hand. Right now, in the time it takes to read this sentence, something is pouring through it. Invisible particles, trillions of them, every second, streaming through your skin, your bones, your beating heart, and out the other side without leaving a single scratch. We call them neutrinos. The name means the little neutral one, and they are the shyest things in the universe. Most of them come from the sun. Deep in its core, the sun burns by fusing hydrogen, and every fusion spits out these tiny ghosts. They cross 93 million miles of empty space, reach the Earth, and plunge straight through the whole planet as if it were made of glass. About 100 trillion of them pass through your body every second. In your entire life, only a handful will ever bump into a single atom inside you. Think about what that means. You could stack lead a light year thick, a wall of solid metal reaching almost to the nearest star, and a neutrino would have a fair chance of sailing clean through it. To a neutrino, the Earth is a ghost. To a neutrino, you are a ghost. They live in the same space we do, and almost never notice we are here. This is why, for a long time, nobody could prove they were real. You cannot see them. You cannot feel them. They carry no electric charge, so they ignore magnets and wires and every instrument built to catch ordinary particles. They slip through the finest net physics ever made, and yet we know they exist. We know it because when we finally learned to catch even 1 in a million, the universe started to make sense in a way it never had before. Neutrinos turned out to be woven into the death of stars, the birth of elements, the reason the sun shines at all. But here is where the story turns strange. For nearly a century, physicists believed there were exactly 3 kinds of neutrino, 3 flavors, no more. The math seemed to close. The books seemed to balance. Every experiment agreed. Then the numbers started to slip. Tiny gaps, small deficits, handfuls of particles that appeared where they should not, or vanished where they should have stayed. Alone, each gap looked like a mistake, a rounding error, a bad night in the lab. But they kept coming, from different machines, in different countries, run by people who had never spoken to each other, and they all pointed at the same impossible thing, a 4th neutrino, one even shyer than the 3 we know. One so withdrawn it feels no forces at all, not even the feeble one that lets ordinary neutrinos flicker into being, a particle that would touch nothing, ever, except through gravity. The rules of physics, as we have written them, say this particle cannot be there. There is no room for it. No equation demands it. It would be a stranger that walked in from outside the entire theory. We call it the sterile neutrino. And right now, in a laboratory buried beneath the border of France and Switzerland, some of the smartest people alive are building traps to catch it. To understand why they would chase something that may not exist, we have to go back to the moment the first ghost was born, in the mind of a desperate man who thought he had ruined physics forever. In the winter of 1930, a brilliant Austrian physicist named Wolfgang Pauli sat down to write a letter that he was almost ashamed of. Physics had a problem, and it was a serious one. The problem was a kind of radioactivity called beta decay. Certain atoms, left alone, would suddenly transform. A particle would shoot out of the nucleus at high speed, and the atom would change into a different element. Scientists could catch that flying particle and measure its energy, and the energy was wrong. There is a law in physics, older and firmer than almost any other. Energy cannot be created. Energy cannot be destroyed. Whatever you start with, you must end with. It is the bedrock. Break it, and nothing in science can be trusted again. But in beta decay, energy went missing. The atom before the decay held a certain amount. The flying particle after the decay carried away less, sometimes a little less, sometimes a lot less, and the missing energy was nowhere to be found. It simply vanished. For years, this haunted physicists. Some of the greatest minds alive began to whisper a terrifying idea. Maybe the sacred law was wrong. Maybe, deep inside the atom, energy really could leak out of existence. Pauli refused to believe it, and so he made a wild bet. What if, he asked, the energy was not missing at all? What if a second particle flew out during the decay, an invisible one, and carried the energy away with it? A particle so small and so quiet that no instrument could see it. A ghost that stole the energy and slipped out unnoticed, balancing the books in secret. It was a clever idea. It was also, by Pauli's own admission, a kind of cheating. He had solved the problem by inventing something that, as far as anyone could tell, could never be detected. And in science, that is dangerous ground. If a thing cannot be measured, cannot be seen, cannot be caught, how is it any different from a thing that is simply absent? Pauli knew this. He reportedly said he had done a terrible thing. He had proposed a particle that could not be found. He was so embarrassed that he did not publish his idea in a proper paper. He wrote it in a letter to a group of physicists at a conference, addressed jokingly to the dear radioactive ladies and gentlemen, and admitted he could not come himself because he had to attend a dance. He called his invisible particle the neutron, but 2 years later, another scientist discovered the heavy neutral particle that sits inside every nucleus and took that name for it. So the little ghost needed a new one. An Italian physicist gave it the name that stuck, the neutrino, the little neutral one. For 26 years, that was all the neutrino was. A patch, a guess, a ghost that everyone believed in because the math was so beautiful with it and so broken without it. Nobody had ever caught one. Nobody knew if they ever could. Pauli himself doubted it would happen in his lifetime. He had built the perfect suspect and left behind no way to arrest it. Then, in a swampy corner of South Carolina, 2 Americans decided to try the impossible. They were going to catch a particle that could pass through the entire Earth. And to do it, they first considered setting off a nuclear bomb. Frederick Reiners and Clyde Cowan had a problem that sounded like a joke. They wanted to detect a particle that hardly ever touches anything. Their solution was to find a place with so many neutrinos pouring out that even a tiny fraction interacting would be enough. Their first idea was breathtaking. They would put a detector next to an exploding atomic bomb. A nuclear blast releases a colossal burst of these ghosts in a fraction of a second. Drop a detector down a shaft near the explosion, catch the flash, and run. They were serious. The plan was approved. Then someone suggested something calmer. A nuclear reactor also floods its surroundings with ghosts, quietly, all day and all night. And it does so without blowing anything up. So the 2 men took their experiment to the Savannah River plant in South Carolina, set up beside a running reactor, and got to work. Here is the beautiful trick they used. A reactor pours out anti-neutrinos, the mirror image version of the ghost. Reiners and Cowan built a tank filled with water, laced with a special chemical. Once in a great while, an anti-neutrino from the reactor would strike a proton in that water. The collision would produce 2 new particles, and each one would leave a signal. The first signal came almost at once, a flash of light, sharp and clean. Then, a few millionths of a second later, a second flash, as one of the new particles was swallowed by an atom in the chemical they had added. 2 flashes, separated by a precise, tiny gap of time. Only a neutrino made that exact double heartbeat. It was a fingerprint, a signature, proof that a ghost had passed through and, for once, touched something. For months they watched. They filtered out false alarms. They shielded against stray radiation. They chased down every other thing that might fake the double flash. And the signal held. The heartbeats kept coming, steady, unmistakable, exactly as the theory predicted. They had done it. They had caught a particle that could fly through a light year of lead. They had reached out and grabbed one of Pauli's ghosts. They sent him a telegram. It told him, plainly, that they had detected the particle he had invented 26 years earlier and had feared no one ever would. Pauli, the man who thought he had done a terrible thing, celebrated. The story goes that he opened a case of champagne and drank it with friends. The ghost was real. The desperate guess had been right, and a law of nature that had trembled on the edge of collapse was saved. But catching the neutrino was only the beginning of the trouble it would cause. Because once physicists could study these particles, they started asking harder questions. How many kinds were there? Where did they come from? And why did they behave so oddly, refusing to fit neatly into the tidy picture everyone was building? The first shock was simple to state. The neutrino Reiners and Cowan caught had a hidden sibling. There was a second kind. And then, years later, a third. Each one paired with a different partner particle, each one slightly different from the others. 3 ghosts, not one. That seemed to be the full set. Physicists drew up their grand table of particles, wrote in 3 neutrinos, and considered the matter closed. They were about to learn that the sun itself disagreed. By the middle of the last century, physicists had a new obsession. How many kinds of neutrino were there? The first kind, the one born in beta decay and caught beside the reactor, came paired with the electron. Whenever this neutrino interacted and turned into something you could see, an electron popped out. So they called it the electron neutrino. Then came a surprise. In the wild, there is a heavier cousin of the electron called the muon. It behaves almost exactly like an electron, just fatter and short-lived. And when physicists studied certain reactions, they found a neutrino that always produced a muon when it interacted, and only a muon. That made sense only if this was a different neutrino. A second flavor, the muon neutrino. An experiment in 1962 proved it. Fire a beam of these ghosts at a detector, and out came muons, only muons. The electron neutrino and the muon neutrino were genuinely separate things. 2 flavors confirmed. Then physics found a third heavy cousin, heavier still, called the tau. And by the logic that had worked twice already, everyone expected a third neutrino to go with it, the tau neutrino. It took until the year 2000 for a detector to finally catch one directly, but few doubted it was there. So the family was complete. 3 charged partners, the electron, the muon, and the tau. 3 matching ghosts, 1 for each. A neat, closed set. But how could anyone be sure there were only 3? Maybe there was a 4th flavor hiding somewhere, too heavy or too shy to show up in the experiments of the day. The answer came from a machine in Europe that did something clever. It built a particle so heavy and so short-lived that it decayed almost instantly into other things, including neutrinos. The rate at which this particle fell apart depended on how many kinds of light neutrino existed for it to decay into. More flavors, faster decay. Fewer flavors, slower decay. They measured that decay with exquisite care, and the number it gave back was clear, 3. There were 3 kinds of light neutrino that behaved the normal way, that felt the ordinary forces, that took part in the usual reactions. Exactly 3, no more and no fewer. This measurement was rock solid, and it still stands today. Any 4th neutrino, if it exists, cannot be a normal one. It cannot feel the weak force the way the others do. It would have to be something else entirely, something that hid from this experiment by refusing to join in at all. Hold on to that clue, because it becomes the whole heart of this story. The universe told us, loud and clear, that there are exactly 3 ordinary neutrinos. Any extra one would have to be extraordinary, silent even by neutrino standards. A ghost among ghosts? For a while, none of this seemed urgent. 3 flavors were enough to explain what people saw. The table was full. The theory worked. And then astronomers pointed their strangest detectors at the sun, counted the ghosts streaming out of it, and got an answer that was flatly, stubbornly wrong. 2 out of every 3 neutrinos the sun should have been sending us were simply not arriving. something was happening to them on the way, something nobody had predicted, and solving that mystery would crack open the whole neat picture of three tidy flavors and reveal that neutrinos were far stranger than anyone had dared to think. Deep underground, in an old mine, sat a tank the size of a swimming pool, filled with cleaning fluid. It was one of the strangest scientific instruments ever built, and its only job was to count the ghosts coming from the sun. The idea was simple. The sun makes electron neutrinos by the unimaginable trillion born in the fusion fires at its core. A tiny number of them, passing through that giant tank, would strike an atom and leave a trace. Count the traces, and you count the sun's neutrinos. Compare that to how many the sun should be making, and you get a beautiful check on whether we truly understand how stars shine. For years, the experiment ran, and year after year, it returned the same maddening result. The ghosts were missing. About a third of the expected number showed up. The other 2/3 were gone. This was a crisis. Either we did not understand the sun, or we did not understand the neutrino, and both options were frightening. Scientists checked the tank. They checked the fluid. They checked the sun's models, the fusion rates, the temperatures at its core. Everything held up. The sun should have been sending a certain flood of neutrinos. The Earth was catching only a trickle. People called it the solar neutrino problem, and it sat unsolved for decades. Some suspected the detector was flawed. Some suspected the theory of the sun was off. A few brave thinkers suspected something far more radical. Maybe the neutrinos were leaving the sun exactly as predicted, and something happened to them during the 8-minute journey to Earth. Maybe they were changing on the way. That idea sounded almost absurd. A particle is what it is. An electron neutrino should stay an electron neutrino. It should not be able to turn into something else in mid-flight. But that detector in the mine had a blind spot, and it mattered enormously. It could see only electron neutrinos. If a solar neutrino somehow morphed into a muon or tau neutrino along the way, the tank would be blind to it. The ghost would arrive, sail through, and never register. From the detector's point of view, it would simply have disappeared. So there were two possibilities. Either the sun was making far fewer neutrinos than we thought, which would mean our understanding of stars was badly broken, or the neutrinos were shape-shifting in flight, arriving in disguises the detector could not recognize. To settle it, physicists needed a new kind of detector, one that could see all three flavors at once, one that could catch the muon and tau neutrinos as well as the electron ones. If that detector found the missing 2/3 hiding in the other flavors, the mystery would be solved. The sun would be innocent, and the neutrino would be revealed as something stranger than anyone had imagined. They built it deep in a mine in Canada, a giant sphere filled with heavy water, watched by thousands of light sensors staring inward like eyes in the dark. And when they finally added up every flavor of ghost arriving from the sun, the total matched the prediction perfectly. All of it, every last neutrino. The sun was making exactly as many neutrinos as the theory said. The missing 2/3 had been there all along, wearing different faces, which meant the impossible thing was true. Neutrinos change, and a particle that can change its identity is hiding a secret that shatters the rulebook. The discovery had a name that sounds almost gentle: neutrino oscillation. What it describes is anything but gentle. It means a neutrino does not have one fixed identity. It cycles through them. Picture a neutrino leaving the sun as an electron neutrino. As it races through space, it begins to blur. Partway through its journey, it is a blend, part electron flavor, part muon, part tau. A little further on, the blend has shifted again. It sloshes back and forth between the three flavors, over and over, as it flies. Catch it early, and it might look like an electron neutrino. Catch it later, and the very same particle might behave like a muon neutrino instead. This is why the sun's ghosts seem to vanish. They left as one flavor and arrived as a mix. The old detector, tuned to see only one, missed most of them. They had not disappeared, they had changed clothes. How can a single particle be three things at once, cycling between them as it moves? The honest answer lives in the deep strangeness of quantum mechanics, where a particle can exist as a combination of possibilities until something forces it to pick one. But there is a way to picture it. Imagine three musical notes played together as a chord, each at a slightly different pitch. The combined sound swells and fades in a slow, rolling beat. It surges, softens, surges again. Nothing is added and nothing removed. The beat comes purely from the three notes, drifting in and out of step with each other. A neutrino is like that chord. Its three flavors ripple in and out of phase as it travels, and which flavor you find when you catch it depends on where in that rolling beat you happen to look. Two physicists, working on detectors in Japan and Canada, nailed this down with such care that they shared a Nobel Prize for it. One watched ghosts born in the atmosphere and saw them change flavor depending on how far they had traveled. The other caught the sun's neutrinos in that giant sphere of heavy water and proved the missing flavors were simply in disguise. Together they turned a wild guess into settled fact. Neutrinos oscillate. The universe agrees. It has been confirmed with ghosts from the sun, from the sky, from reactors, from particle beams fired hundreds of miles across countries. The evidence is overwhelming, and it should have been a triumph, pure and clean. The solar mystery was solved. The sun was vindicated. The neutrino was understood at last. But every physicist who understood oscillation felt a chill at the same moment, because oscillation carries a hidden implication, a quiet consequence that tears a hole in the most successful theory in the history of science. For a neutrino to oscillate, for it to slosh between flavors on its journey, it must obey one strict condition. It has to have mass. Even a whisper of mass, the tiniest sliver, but greater than zero. A truly massless particle cannot oscillate. It would fly frozen in a single identity forever. So the fact that neutrinos change proves that neutrinos weigh something. That sounds harmless. It is the opposite, because the grand theory that physicists had spent 50 years building, the theory that got almost everything right, made one flat prediction about neutrino mass. It said there was none, zero. Neutrinos, it insisted, must be massless. Oscillation proved the theory wrong, and that crack would grow into the doorway through which a forbidden fourth ghost might one day walk. The most successful theory in all of physics has a modest name, the Standard Model. It is the rule book of reality, the description of every known particle and nearly every force that binds them. It has been tested to a precision that beggars belief, predicting some numbers correctly to more decimal places than you can casually count. When physicists talk about it, they use words usually reserved for cathedrals. And it made a clear, confident claim about the neutrino. The neutrino has no mass. It is a massless thing, flying forever at the speed of light, weightless as light itself. Oscillation broke that claim in half. To understand why this matters so much, you have to understand how the Standard Model gives mass to anything at all. Particles get their mass by dragging against a field that fills all of space. Some particles grab that field hard and become heavy. Others barely touch it and stay light. But the grabbing works only if the particle comes in two versions, a left-handed one and a right-handed one, and the field can link the two together. Here is the strange thing about neutrinos. In every experiment ever done, every neutrino spins the same way. They are all, in a sense, left-handed. A right-handed neutrino has never been seen, not once. And that is the trap. With no right-handed neutrino, the usual machinery that grants mass has nothing to grab. The field cannot link a left-handed neutrino to a right-handed partner that does not exist. So in the Standard Model, as originally written, the neutrino is stuck being massless. But it is not massless. Oscillation proves it weighs something. So the neutrino gets its mass by some route the Standard Model did not include, a route that was left out, a missing chapter. There are two leading ideas for how a neutrino could weigh anything. and both of them are astonishing. The first idea says the missing right-handed neutrino does exist. It is simply so shy, so withdrawn, that no experiment has ever caught it. It would be a neutrino that ignores the weak force entirely, that takes part in nothing, that hides completely. If it exists, it could link up with the ordinary neutrino and grant it the tiny mass we observe. A right-handed neutrino that feels almost nothing, a ghost among ghosts. This is the sterile neutrino, and here it is again, sliding out of the equations, offered up as the solution to why neutrinos weigh anything at all. The second idea is even stranger, and we will come to it. But notice what has happened. The neat table of 3 flavors, closed and complete, has sprung a leak. The theory that said neutrinos are massless was wrong, and the most natural fix, the one that makes the math sing, requires a particle the theory has no room for. The universe handed physicists a fact they did not ask for. Neutrinos have mass, and every attempt to explain that fact keeps summoning the same uninvited guest. The sterile neutrino is now far more than a patch for a few odd measurements. It has become a candidate answer to one of the deepest questions in physics. Why does anything weigh what it weighs? To chase it, though, physicists first had to understand exactly what made it so impossible to catch. And that comes down to a single, dizzying fact about which direction a particle spins. Every particle that spins has a kind of handedness. Picture a spinning bullet flying toward you. If it spins one way as it moves, we call it right-handed. If it spins the other way, left-handed. It is a simple property, and most particles come in both versions. A left-handed electron and a right-handed electron both exist. The universe uses both freely. Neutrinos break this pattern in the most jarring way imaginable. Every neutrino ever detected is left-handed. Every antineutrino ever detected is right-handed. The mirror versions, right-handed neutrinos and left-handed antineutrinos, have never once shown up. In all the ghosts caught across 70 years of experiments, this rule has held without a single exception. This is one of the eeriest facts in physics, and it is easy to walk past without feeling its weight. So sit with it. Nature, which seems so even-handed, so willing to use left and right in equal measure, draws a hard line for the neutrino. It picks one hand and forbids the other. Why should the universe care which way a ghost spins? The reason reaches into the machinery of the weak force, the feeble interaction that lets neutrinos exist and change in the first place. That force is built to touch only left-handed particles and right-handed antiparticles. It is blind to the rest. So, a right-handed neutrino, even sitting right in front of the weak force, would be invisible to it. The force would reach out and feel nothing. Now follow that thought to its edge. A right-handed neutrino would ignore the weak force. It carries no electric charge, so it ignores electricity and magnetism. It has no color charge, so the strong force that binds atomic nuclei means nothing to it. That leaves only gravity, the faintest force of all, tugging on it through its tiny mass. A particle like that would be almost perfectly alone. The ordinary neutrino is already the shyest thing we know, interacting through only one weak force. Strip away even that, and you get something that touches the universe through gravity alone. It would pour through detectors, through planets, through stars, and register nothing because there is nothing for our instruments to grab. This is what physicists mean when they say sterile. The word here means barren, cut off, unable to join in, like soil that grows nothing. A sterile neutrino would feel no force that any detector can use. It would be the ultimate ghost, a particle that exists and yet declines to participate in almost everything. And this creates a maddening puzzle. If such a particle interacts with nothing we can measure, how could we ever prove it is there? You cannot build a detector to catch something that refuses, by its very nature, to be caught. The answer, when physicists found it, was devilishly clever. You do not catch the sterile neutrino directly. You catch the ordinary neutrinos and watch them for a betrayal. Because if a sterile neutrino exists, the 3 normal flavors would do more than oscillate among themselves. Once in a while, One of them would flicker into the sterile state and vanish from view, then perhaps flicker back, a ghost slipping out a hidden door and returning. Watch enough ordinary neutrinos closely enough, and you might catch them disappearing into that door or arriving through it. The sterile neutrino would leave its fingerprint on the behavior of its ordinary cousins, where any instrument can read it. And in 1995, in a desert laboratory in New Mexico, an experiment saw exactly the kind of fingerprint that a hidden door would leave. In the early 1990s, at Los Alamos National Laboratory in the high desert of New Mexico, an experiment went looking for oscillation up close. Most oscillation happens over long distances. The sun's neutrinos travel millions of miles before they change. But if a fourth, heavier neutrino existed, it would cause a faster kind of oscillation, one that showed up over just a few dozen feet. This experiment was built to catch that quick flicker. The setup was direct. A particle accelerator produced a beam rich in muon antineutrinos. A tank of special liquid sat a short distance away, watching. The muon antineutrinos should have stayed muon antineutrinos over that short hop. The three ordinary flavors changed too slowly to matter across such a tiny gap. So if electron antineutrinos started appearing in the tank, something unusual was speeding up the change. They appeared. More electron antineutrinos arrived than the ordinary picture allowed. A small excess, but a stubborn one. The team counted, checked, recounted. The extra ghosts would not go away. The simplest explanation was a fast oscillation, driven by a fourth neutrino far heavier than the known three, a sterile one, reaching in from outside the theory, giving the muon antineutrinos a quick nudge into electron flavor. It was the first real hint that Paulie's family might have a hidden member. But one experiment is never enough, especially for a claim this large. A single strange result can come from a flaw nobody noticed, a background nobody accounted for, a quirk of one particular machine. Extraordinary claims demand more. The whole community wanted this signal either confirmed by a completely different experiment or explained away. There was also a problem that made physicists uneasy. The kind of sterile neutrino this result pointed to had a specific weight, and that weight caused trouble elsewhere. Other experiments, watching neutrinos over different distances, should have seen matching effects, and they mostly did not. The desert signal sat awkwardly, refusing to line up cleanly with everything else. It was either a revolution or a mistake, and nobody could tell which. So the result hung in the air, unresolved, for years. Too strong to ignore, too lonely to trust. A single crack in the wall, and no way to know if the whole wall was about to come down or if it was just a scratch in the paint. The only way forward was to build a bigger, better experiment. One aimed squarely at this signal, designed to either reproduce that excess or kill it for good. If a second machine, built differently, in a different place, saw the same extra ghosts, the sterile neutrino would move from wild idea to serious discovery. If it saw nothing, the desert result would fade into history as a famous false alarm. That machine was built at Fermilab, near Chicago. It was larger, more sensitive, and it would watch far more neutrinos than the desert experiment ever had. Physicists expected it to settle the question within a few years, one way or the other. Instead, it deepened the mystery beyond anything they had imagined. It ran for a decade and a half. It gathered a mountain of data, and when the numbers came in, they did not simply confirm the desert anomaly or dismiss it. They found an even bigger excess. And they found it in a way that made the sterile neutrino harder to accept and harder to reject at the same time. The experiment was called Mini Boone, and for 15 years it watched a beam of muon neutrinos with relentless patience. Its mission was to test the desert anomaly. If a sterile neutrino was speeding up oscillation, then muon neutrinos in the beam should occasionally turn into electron neutrinos over a short distance, and Mini Boone would catch the extras. If nothing showed up, the old result could finally be laid to rest. Something showed up, in fact, more than expected. Mini Boone saw a clear excess of electron-like events, hundreds of them beyond what the ordinary theory predicted. When physicists combined this with the old desert result, the two together reached a level of statistical strength that, in particle physics, usually means discovery. The numbers were screaming that something real was there, and yet the room did not erupt in celebration, because Minnie Boone had a weakness that turned its triumph into a riddle. The detector could not always tell the difference between an electron and a photon, a particle of light. Both could leave a similar fuzzy smudge inside the tank. So when Minnie Boone reported an excess of electron-like events, a nagging doubt remained. Were these truly electron neutrinos appearing out of the beam, the fingerprint of a sterile neutrino? Or were they photons, produced by some ordinary process nobody had modeled quite right, wearing an electron's disguise? This mattered enormously. If the excess was electrons, it pointed to a fourth neutrino and new physics. If it was photons, it pointed to a boring mistake in the bookkeeping. The whole revolution hinged on a distinction the detector was not sharp enough to make. There was another thorn. The sterile neutrino that would explain both experiments together had to have a particular mass and a particular strength of mixing with ordinary neutrinos. But other experiments, watching neutrinos vanish rather than appear, kept failing to see the matching effect. If a sterile neutrino were nudging muon neutrinos into electron flavor, it should also make muon neutrinos quietly disappear at a certain rate. Nobody could find that disappearance. The story had a hole in the middle, so by the 2010s, the picture was genuinely bizarre. Two separate experiments, built decades apart, had seen the same kind of excess, and the combined signal was strong. Yet the simplest explanation clashed with a pile of other results, and the detectors that saw the excess could not prove it was made of the right particles. The sterile neutrino was neither confirmed nor killed. It floated in a strange limbo, propped up by real data, undermined by other real data, impossible to prove and impossible to dismiss. And these two beam experiments were only part of the strangeness. While physicists argued over the desert and the Fermilab excess, a completely different set of measurements had been quietly piling up, this time from nuclear reactors and radioactive metals. And they too came up short in the same suspicious direction. 4 separate kinds of anomaly from 4 different sources were now leaning toward the same forbidden particle. Any one of them alone might be a fluke, but together they started to look like a pattern that nature was trying to show us. The next clue came from the humming reactors that power our cities. When physicists counted the antineutrinos pouring out of them, the tally came up mysteriously light. Nuclear reactors are the most generous neutrino factories on Earth that we can walk right up to. Every second, a large power reactor pours out an unimaginable flood of antineutrinos as its fuel splits apart. That makes them perfect laboratories. Park a detector nearby, count the ghosts, and compare the tally to how many the reactor should produce. Around the year 2011, physicists went back and sharpened their prediction for exactly how many antineutrinos a reactor should emit. Then they lined that new, careful prediction up against decades of measurements from detectors around the world. The measurements came up short. Consistently, across many experiments, the detectors caught a few percent fewer antineutrinos than the improved prediction said they should. It was a small gap, only a handful of ghosts missing out of every 100. But it was steady, and it appeared again and again. They called it the reactor antineutrino anomaly, and the shape of it was tantalizing. A few percent of the electron antineutrinos seemed to go missing over short distances, exactly the kind of quiet disappearance a sterile neutrino would cause. If some of the reactor's antineutrinos were flickering into the sterile state and vanishing before they reached the detector, the count would fall short by just about this much. Suddenly, the sterile neutrino had a second kind of evidence. The beam experiments saw electron neutrinos appearing where they should not. The reactors saw electron antineutrinos disappearing where they should not. Appearance and disappearance, 2 sides of the same coin, both pointing at the same hidden particle. For a while, this felt like the walls closing in on a discovery. The case was building. But there was a subtle trap buried in the reactor anomaly, and it took years to spring. The whole thing rested on the prediction, on knowing exactly how many antineutrinos a reactor should make in the first place. And that prediction depended on the messy, complicated details of how uranium and plutonium break apart into hundreds of different fragments, each one spitting out antineutrinos in its own way. What if the prediction was simply wrong? What if the reactors were behaving perfectly and the error was in our sums? That is exactly what began to unravel. Newer experiments studied how the missing fraction changed as reactors burned different mixtures of fuel. If a sterile neutrino was stealing antineutrinos, the shortfall should not care which fuel was burning. But it did care. The deficit tracked the fuel in a way that pointed straight at a flaw in the old calculation, with no new particle needed. The recipe for predicting reactor antineutrinos had been slightly off all along. Piece by piece, the reactor anomaly dissolved. Careful new measurements and better modeling drained away its strength until it faded into statistical noise. What had looked like a second pillar holding up the sterile neutrino turned out to be built on sand. So, one of the 4 clues evaporated. That is how this science works. A hint appears, the community attacks it from every side, and sometimes it survives and sometimes it crumbles. But 3 clues remained, and one of them came from a source so clean, so simple, that it could not be blamed on the tangled chemistry of a reactor. It came from a lump of radioactive metal and a tank of liquid gallium in an experiment designed to be almost impossible to get wrong. That one did not fade. It got stronger. Deep beneath a mountain in Russia sat a tank filled with liquid gallium, a soft silvery metal, and a plan of beautiful simplicity. The experiment worked like this. You take an intense radioactive source, a lump of material that pours out electron neutrinos at a known, calculable rate. You place it right in the middle of the gallium. The neutrinos strike the gallium atoms and convert a few of them, one at a time, into atoms of a different element. Later, you carefully extract those transformed atoms and count them. That count tells you how many neutrinos interacted. The strength of this method is its cleanness. Unlike a reactor, where you must guess how many neutrinos are made, here the source is a known quantity. You can measure exactly how strong it is. There is very little room for the kind of hidden error that plagued the reactor story. The sums are about as solid as physics gets. So physicists ran the experiment, counted the transformed atoms, and compared the result to the neutrinos the source was known to emit. The count came up short again, and by a striking amount, around 1/5 of the expected neutrinos simply missing. And this was no reactor with murky fuel chemistry to blame. This was a known source, a clean method, a straightforward count. The ghosts were vanishing over a distance of just a few feet, inside a tank of metal, and the shortfall was large. The most recent and most careful version of this experiment sharpened the puzzle rather than dissolving it. The deficit held. It even deepened. The neutrinos were disappearing at short range in exactly the way a sterile neutrino would cause, and the usual escape routes, the maybe the prediction is wrong excuses, were mostly closed off. This became known as the gallium anomaly, and it is one of the most stubborn hints in the whole hunt. It refuses to go away. Physicists have poked at the atomic physics, questioned the rates at which the source decays, wondered whether some subtle effect in the gallium itself could be fooling them. Nothing has fully explained it. The missing 5th remains missing. Now, step back and look at the full board. Muon neutrinos appearing as electron neutrinos in the desert and at Fermilab. Electron antineutrinos vanishing near reactors before that clue faded. And electron neutrinos disappearing inside a clean tank of gallium. A clue that only grew firmer with time. Different sources, different methods, different countries. And a suspicious number of them pointing at the same forbidden particle, a 4th neutrino with a weight of about 1 electron volt, mixing faintly with the ordinary 3. Any single anomaly could be a fluke or a flaw. That is why no one anomaly ever settles anything. But when several independent measurements start leaning the same way, physicists feel the ground shift. Coincidence gets harder to believe. The pattern starts to look like a message, and the message was thrilling and terrifying at once. If it was real, there was a new particle in the universe, one the standard model forbade, one that would force a rewrite of the deepest rules. If it was not real, then several careful teams had all been fooled by different errors that happened to point the same way, which is its own kind of mystery. To find out which, physicists needed a reason to take the sterile neutrino seriously beyond a scattering of odd counts. They needed a motive, and the sterile neutrino, it turned out, had 3 of the best motives in all of science. Here is a fact about neutrinos that ought to keep you up at night. They are absurdly, ridiculously light. We know the ordinary neutrinos have a little mass because they oscillate, but that mass is almost nothing. The lightest particle you learn about in school is the electron, and the electron is already feather light. A neutrino is at least 1,000,000 times lighter than that. It sits so close to weightless that for decades, everyone assumed it was. This is no small curiosity. It is a genuine scandal in physics. Every other particle in the family gets its mass from the same field, and their masses, while varied, are at least in a sensible range of one another. The neutrino breaks the pattern by an enormous margin. It is as if you weighed a series of animals, mouse, cat, dog, horse, and then found one creature that weighed less than a single speck of dust. You would not shrug, you would ask what makes it so strange. The most elegant answer physicists have ever found is called the seesaw, and it works exactly like the playground toy it is named after. Picture a seesaw with 2 riders. On one end sits a very heavy partner, a neutrino so massive it has never been made in any experiment. On the other end sits the neutrino we actually see. On a seesaw, when one side goes very high, the other goes very low. The heavier the hidden partner, the lighter the visible neutrino becomes. Push the hidden partner's mass up toward something colossal, and the ordinary neutrino's mass drops toward almost nothing, precisely the featherweight we measure. In this picture, the tininess of the neutrino is a clue rather than an accident. It is the shadow cast by a giant we cannot see. The lighter the ghost, the heavier its hidden twin must be. And what is that heavy hidden partner? It is a right-handed neutrino, the very thing the standard model left out. It is sterile. It feels no weak force, no electricity, no strong force. It sits on the far end of the seesaw, enormous and silent, and its only job is to press the visible neutrino down to a whisper. This is why physicists take the sterile neutrino seriously, even without the anomalies. The seesaw is beautiful. It explains one of the ugliest mysteries in physics, the featherweight neutrino, with a single graceful stroke. And it does so by demanding the existence of exactly the kind of hidden, force-shunning particle the anomalies keep hinting at. There is a catch, and it is worth being honest about. The heavy partner in the classic seesaw could be so massive that we could never hope to make it in any machine we could build. If it weighs as much as 100 billion protons, it lies forever beyond our reach. In that case, the sterile neutrino would explain the featherweight puzzle but stay eternally hidden. But there are versions of the idea where the hidden partner is lighter, within a range we could actually probe. Somewhere between the feather-light anomaly suspect and the impossibly heavy giant of the grandest seesaw, heavy enough to be interesting, light enough to catch. And it turns out that a sterile neutrino in a certain middleweight range would do something even more spectacular than explain neutrino mass. It could be the invisible substance that outweighs every star and galaxy in the cosmos. It could be dark matter itself. Something invisible is holding the galaxies together. When astronomers weigh a galaxy by counting its stars, they get one number. When they weigh the same galaxy by watching how fast it spins, they get a number 5 or 6 times larger. Galaxies rotate so quickly that they should fly apart, flinging their stars into the dark, yet they hold. Something we cannot see is gripping them, providing the extra gravity, outweighing all the visible matter many times over. We call it dark matter, and it is one of the greatest unsolved problems in science. It makes up most of the matter in the universe. It shapes how galaxies form, and we have no idea what it is. Whatever it is, it gives off no light, feels no electromagnetism, and drifts through ordinary matter like a fog through a fence. Read that description again. Gives off no light, ignores electromagnetism, passes through ordinary matter almost untouched. That is the profile of a ghost. And there is a ghost in this story that fits it eerily well. A sterile neutrino, if it had the right weight, would be a nearly perfect dark matter suspect, a middleweight version, heavier than the featherweight anomaly suspect, and far lighter than the colossal giant of the grandest seesaw, a few thousand times heavier than an ordinary neutrino, yet still tiny by any normal standard, heavy enough to move slowly and clump together under gravity, silent enough to have hidden from us this whole time. A vast, cold swarm of them could fill every galaxy, unseen, holding the stars in their orbit. This idea is beautiful because it solves two mysteries with one particle. The same hidden neutrino that explains why ordinary neutrinos are so light through the seesaw could also be the dark matter that binds the cosmos. One stranger, two of the deepest holes in physics filled at once. But a sterile neutrino playing the role of dark matter would not be perfectly silent, and that faint imperfection is our best hope of catching it. Even a truly sterile particle can, very rarely, decay. A dark matter sterile neutrino, drifting through space, would occasionally fall apart, and when it did, it would release a single, specific flash of light, a particle of X-ray radiation with a precise energy set by the neutrino's mass. Every one of them across a whole galaxy would emit the very same color of X-ray. Add up trillions upon trillions of these rare decays, and you would get a faint, sharp glow at one exact energy, coming from wherever dark matter gathers. So astronomers began scanning galaxies and clusters with X-ray telescopes, hunting for an unexplained line at a single energy, a glow that ordinary matter could not produce. A few years ago, some teams reported a faint, mysterious signal at a particular X-ray energy coming from galaxy clusters. It set the field on fire. Could this be the death glow of dark matter, the fingerprint of a sterile neutrino finally caught in the act? The signal has proven maddeningly hard to confirm. Some searchers see hints of it. Others, looking where it should be strongest, see nothing. It hovers at the edge of detection, neither confirmed nor ruled out. Another tantalizing maybe in a story full of them. But if the sterile neutrino can explain the featherweight neutrino and the dark matter that binds galaxies, it may reach even further back to the single most consequential question anyone can ask. Why is there anything here at all? You exist. That sounds obvious. It should be impossible. In the first instant after the Big Bang, the universe made matter and antimatter in almost perfect balance. For every particle of matter, an antiparticle. And matter and antimatter are mortal enemies. When they meet, they destroy each other completely, converting themselves into a flash of pure light. If the balance had been exact, every particle would have found its antiparticle, and the two would have annihilated, leaving a universe filled with nothing but light, no stars, no planets, no you. Yet here we are, in a universe made overwhelmingly of matter, with almost no antimatter anywhere. Something tipped the scales. Something, in that first blazing instant, made a tiny bit more matter than antimatter. The imbalance was minuscule, about one extra particle of matter for every billion matched pairs. When the great annihilation swept through and destroyed all the pairs, that one lonely survivor in every billion was left behind. And that surviving residue, that one part in a billion, is everything. Every galaxy, every star, every atom in your body is the leftover from a near-total annihilation. What tipped the scales? This is one of the deepest questions in all of physics, and one of the leading answers points straight at the sterile neutrino. The idea has a name, leptogenesis, and the story it tells is grand. In the earliest moments, The universe was hot enough to create the heavy, sterile neutrinos, the massive hidden partners from the seesaw. These giants were unstable, and they decayed. And here is the crucial part. If their decays were even slightly lopsided, if they produced a tiny bit more matter than antimatter, they would have seeded the universe with a small surplus of ordinary matter. That surplus, once created, would survive. Later processes would convert it into the excess of particles we see today, the 1 in a billion overhang that became all of visible reality. In this picture, we owe our entire existence to the way a hidden, forbidden particle fell apart in the first sliver of time. If leptogenesis is right, then the reason there is something rather than nothing, the reason matter won its war against antimatter, is the sterile neutrino. The same particle that would explain the featherweight neutrino, the same particle that could be dark matter, may also be the reason the universe is not an empty bath of light. It would be the author of existence itself. This is why physicists cannot let the sterile neutrino go. Even when the anomalies wobble, even when one clue fades, the theoretical pull is overwhelming. A single particle that could explain neutrino mass, dark matter, and the survival of matter is not something you walk away from because a few counts came up ambiguous. Of course, leptogenesis works most naturally with the very heavy sterile neutrinos, the ones that might lie forever beyond any machine. But there are careful versions of the theory where the responsible particles are lighter, sitting in a range we could actually reach. In those versions, the particle that made the universe possible could be created and studied in a laboratory on Earth, which raises a staggering thought. The origin of matter might be reproducible. The ghost that saved existence might be catchable. And several of the world's most powerful laboratories are now racing to do exactly that. But before we follow them into their tunnels and beamlines, we have to face the hardest problem of all. How do you catch a particle whose entire nature is to escape? Every hunt in this story runs into the same wall. The sterile neutrino, by its very nature, is built to escape. It feels no weak force, so it slips past the detectors that catch ordinary neutrinos. It carries no charge, so magnets and wires ignore it. You cannot point an instrument at it and wait for a signal, because there is no signal for the instrument to receive. So physicists gave up trying to catch it directly. Instead, they learned to hunt it by its absence and by its shadow. The absence method works like this. You take a beam of ordinary neutrinos and you count them carefully at one distance, then count them again farther away. The three normal flavors will oscillate among themselves in a known, predictable pattern. But if a sterile neutrino exists, some of the ordinary neutrinos will occasionally flicker into the sterile state and vanish from view. Your count will come up short in a specific way, at a specific distance, that the three-flavor picture cannot explain. The ghost betrays itself by making its cousins disappear. This is why the anomalies matter so much, and why they are so agonizingly hard to settle. Every one of them, the desert excess, the reactor shortfall, the gallium deficit, is a story about ordinary neutrinos appearing or disappearing by a little more than they should. None of them catches the sterile neutrino. All of them catch its footprints in the mud, and footprints are treacherous. A small excess or shortfall can come from a sterile neutrino, or from a flaw in the prediction, or from a background nobody modeled, or from a detector that cannot quite tell one particle from another. That is the curse that hung over Mini Booney, unable to distinguish an electron from a photon. That is what dissolved the reactor anomaly, a prediction slightly wrong. To trust a footprint, you have to rule out every ordinary thing that could have made it. This is the deep frustration of the whole field. For 30 years, the sterile neutrino has lived in a maddening middle ground. The hints are real. Careful people, using good machines, keep seeing deviations that lean the same way. But every hint comes wrapped in doubt, and no single experiment has been sharp enough to convert a footprint into a capture. What physicists needed was a detector that removed the doubt, one that could look at each event and say, with confidence, this is an electron and not a photon. This neutrino truly vanished and was not merely miscounted, a machine precise enough to tell a real ghost from an ordinary mistake. Building that machine became a mission in itself. It required a new kind of detector, filled with a special liquid that could photograph the path of every particle in exquisite detail, tracing each track like a wire glowing in the dark, revealing exactly what kind of particle had passed through. They filled a giant vessel with liquid argon, chilled it until it was a cold, clear pool, and wired it to see the faint trails that particles leave as they slice through. With it, the old ambiguities would fall away. An electron would look like an electron, a photon would look like a photon, and the ghost, if it was real, would finally have nowhere left to hide its footprints. The experiment was called Microbuni. It was aimed straight at the heart of the anomaly, and its verdict would land like a hammer. To understand why Microbuni was such a breakthrough, you have to understand what makes liquid argon special. Argon is a gas in the air around you, one of the most common gases you breathe. Chill it far below freezing, and it becomes a clear liquid. Fill a large tank with it, thread it with sensitive wires, and something remarkable happens. When a charged particle races through the liquid, it knocks electrons loose from the argon atoms all along its path. A strong electric field inside the tank sweeps those freed electrons toward the wires, which record exactly where and when each one arrived. The result is like a photograph of the particle's journey. You see far more than the fact that something passed through. You see the precise track it carved, curving and branching, every twist recorded. From the shape and thickness and behavior of that track, you can read what kind of particle made it. This was the exact power Mini-Buni had lacked. In the old experiment, an electron and a photon both left a fuzzy smudge, indistinguishable, and that ambiguity poisoned the whole result. In liquid argon, the two look different. An electron begins its track right where the neutrino interacted. A photon travels a short, invisible distance first, then suddenly blooms into view a little gap away from the interaction point. That tiny gap is the tell. It lets physicists separate the two cleanly, event by event. So, Microbuni was built to sit in the same beam and answer the question Mini-Buni could not. Those hundreds of extra electron-like events, the ones that fueled 30 years of sterile neutrino dreams, were they really electrons, the signature of a fourth neutrino? Or were they photons from some ordinary process, wearing an electron's mask? The detector was a marvel of patience and precision. A large tank of liquid argon, held at bitter cold, watched by rows of wires reading out the ghostly tracks. It sat in the beam at Fermilab and gathered data for years, photographing every interaction, sorting electrons from photons with a clarity no earlier experiment in that beam had possessed. The stakes could hardly have been higher. If Microbuni saw an excess of genuine electrons, it would confirm that something extraordinary was happening in the beam, breathing new life into the sterile neutrino and pointing toward a rewrite of the standard model. If it saw the excess but found it was made of photons, the anomaly would collapse into an ordinary misunderstanding, and if it saw the electrons but could match them to no sterile pattern at all, the mystery would only deepen. The whole field held its breath. This was the experiment that was supposed to end the argument, to take the most famous anomaly in neutrino physics and either crown it or bury it. Decades of hints, 4 separate clues, 3 profound motives, all of it now hinging on what a cold tank of argon had recorded as the beam poured through. The first results arrived, and then, over several years, a fuller and more powerful analysis followed, drawing on more data and sharper methods. Physicists combed through the tracks, counted the true electrons, and tested them against the sterile neutrino's predicted pattern. And what they found did not crown the ghost. It did not quite bury it either. It did something stranger and more unsettling than anyone had prepared for. In the final months of 2025, the Microbuni team delivered their most complete answer, and the news traveled fast through the world of physics. The simplest, most popular version of the sterile neutrino, the one that had reigned as the favorite explanation for 30 years, was ruled out. Their careful, high-resolution look at the beam found no sign of the oscillation that a single light, sterile neutrino would produce. The tracks in the argon, sorted and counted with a precision the old experiments could only dream of, did not match the pattern the ghost was supposed to leave. Where the theory predicted electron neutrinos appearing at a certain rate over a certain distance, Microbuni saw no such appearance. The disappearance a sterile neutrino should cause was absent too. Across the region of possibility where this particle was most expected to live, the detector looked hard and came up empty. One of the leaders of the experiment called it a kind of paradigm shift. For a generation, whenever a neutrino experiment saw something it could not explain, the sterile neutrino was the first suspect anyone reached for. It was the reflexive answer, the comfortable guess. Microbuni, with its sharp new eyes, closed the door on the simplest form of that guess. This was a real result, and a hard one for many to swallow. 30 years of hope had gathered around this particle. Careful people had built careers on the anomalies, had believed a discovery was near, and now the cleanest experiment yet, the one everyone had waited for, said the obvious version of the story was wrong. It fit with other bad news for the light sterile neutrino arriving around the same time. A separate experiment watching muon neutrinos travel a few hundred meters saw no sign of the disappearance the ghost should cause. The reactor clue had already faded. One by one, the pillars supporting the featherweight sterile neutrino were being knocked down. You might think this ends the story. The ghost was chased, cornered, and found to be a mirage. Case closed. It is emphatically not closed, and this is the part that makes the whole saga so extraordinary. Because Microbuni, in ruling out the sterile neutrino as the cause, did not explain the original anomaly away. Remember what started all this. Minibuni saw an excess of electron-like events it could not account for. Microbuni was built to find out what those events really were, and when it looked, it confirmed something unsettling. The excess is real. There genuinely are extra events there. They are simply not caused by the sterile neutrino in the way everyone assumed. So the anomaly survived the death of its own best explanation. The mysterious excess is still sitting in the data, unexplained, its favorite suspect eliminated, no clear replacement in sight. The hunters had spent 30 years chasing a specific ghost down a specific hallway. Microbuni turned on the lights and showed the hallway was empty, but the thing that had been making the noises was still somewhere in the house, and that leaves physicists in the strangest position of all. The simplest sterile neutrino is fading, yet the mysteries that summoned it, the anomalies, the featherweight mass, the dark matter, the origin of existence, are all still there, still demanding an answer. Maybe the ghost is real, but wears a different mass than anyone guessed. And there was another experiment, of a completely different design, closing in on exactly that possibility from the other side. While the beam experiments chased the sterile neutrino by watching particles appear and disappear, a completely different machine in Germany went after it another way. Instead of watching neutrinos travel, it decided to weigh them, one radioactive decay at a time. The experiment is called Katrin, and it is a monster. At its heart is a vast vessel, a stainless steel tank the size of a small blimp, one of the largest ultra-high vacuum chambers ever built. Its purpose is to measure something almost unmeasurably delicate, the exact energy of electrons flying out of decaying atoms, measured so precisely that the faint tug of the neutrino's mass becomes visible. Here is the idea. Katrin uses tritium, a heavy, radioactive form of hydrogen. Tritium atoms decay, and each decay throws out an electron and a neutrino, sharing the released energy between them. The neutrino escapes unseen, as always, but it carries away energy, and the amount it carries depends on its mass. By measuring the electrons with fanatical precision, catching the tiny ceiling on how much energy they can have, Katrin can read off the weight of the neutrino from the shape of the electron spectrum. Now, here is how it hunts the sterile neutrino. If a fourth, heavier neutrino exists and mixes with the ordinary ones, then sometimes a tritium decay would produce that heavier ghost instead. And because it is heavier, it would leave a tiny, sharp kink in the pattern of electron energies, a little step in the curve at a specific place. Find that kink and you find the sterile neutrino. Its weight would be written directly into the energies of the electrons. This approach is beautiful because it sidesteps the ambiguities that haunted the beam experiments. CERN does not have to tell an electron from a photon. It does not depend on murky predictions of how many neutrinos a reactor makes. It just counts electrons and measures their energy, over and over, millions upon millions of times, and looks for a distortion that only a sterile neutrino could carve. The scale of the counting is staggering. By the time it finished a major phase of data taking, CERN had recorded well over 200 million electrons in the crucial region of the spectrum, each one a tiny vote on the neutrino's mass. With that mountain of data, it could probe mixings and masses that earlier experiments could not touch, pushing into new territory for the sterile neutrino. And CERN could reach places the beam experiments could not. It was sensitive to sterile neutrinos across a wide range of possible weights, including some that the desert and reactor anomalies could never test. It was a fresh pair of eyes, looking for the same ghost from a completely new angle, using a completely different method, vulnerable to completely different errors. This is exactly how physics is supposed to corner an elusive truth. You attack it from many directions at once. If a beam experiment and a weighing experiment, built on totally different principles, both point at the same particle, the case becomes hard to deny. And if both come up empty, the ghost has fewer and fewer places to hide. The world waited for CERN's verdict on the sterile neutrino, hoping that where the beams had wavered, the great steel tank might finally see something clear. What it saw was nothing, and that nothing, arriving at the very same time as microboonies, tightened the noose on the light sterile neutrino from two directions at once. In the same season that Microboony delivered its verdict, CERN published its own. The two results landed almost together in the same prestigious journal, and they told a matching story. CERN found no sterile neutrino. Across the range of weights and mixings it could probe, the great steel tank saw no kink in the electron spectrum, no telltale step, no distortion that a fourth neutrino would carve. The pattern of electron energies matched the ordinary three-flavor picture. Where a sterile neutrino should have left its signature, the curve was smooth and clean and empty. CERN pushed its limits below where earlier searches had reached, and still, nothing appeared. Two experiments, built on utterly different principles, hunting the same ghost, both came back empty in the same few weeks. One watched neutrinos in a beam and saw no oscillation into the sterile state. The other weighed neutrinos in decaying atoms and saw no hidden heavy cousin. Different methods, different countries, different possible errors, the same silence. Physicists have a phrase for a moment like this: two strikes for the light sterile neutrino. The featherweight version of the ghost, the one that would explain the desert and reactor and gallium anomalies through a fourth neutrino of about 1 electron volt, was running out of room to exist. Its favorite hiding places were being sealed off, one by one. It is worth pausing to admire what is happening here, because it is science working exactly as it should. A tantalizing idea appeared, backed by real hints. The community did not fall in love with it and stop looking. It built better and better machines, aimed them at the idea from every possible angle, and demanded that the idea prove itself. When the sharpest experiments looked and found nothing, they said so plainly, even though many had hoped for a discovery. The ghost was not spared because people wanted it to be real. So, is the sterile neutrino dead? The light one, the version tied to the classic anomalies, is on very thin ice. That much is clear. But this is where you must be careful, because dead is a strong word, and the story is more subtle than a simple defeat. First, the anomalies themselves have not all vanished. The gallium deficit, that stubborn missing fifth of neutrinos in a tank of metal, still stands, still unexplained. Something is going on there, and ruling out the simplest sterile neutrino does not make it disappear. Second, and more important, the sterile neutrino is not a single particle with a single weight. It is a family of possibilities. The experiments so far have mostly closed off the featherweight end, but the sterile neutrino could be far heavier. It could sit in the range that would make it dark matter thousands of times heavier. It could be heavier still, a hefty particle in the range that leptogenesis and the seesaw prefer, heavy enough to explain the origin of matter. Those versions have barely been touched. They live at masses the featherweight searches were never built to reach. The hunters had cleared one room of the house and found it empty. But the house is enormous, and most of its rooms have never been searched. To search them, you cannot use a tritium tank or a short beam. You need something with far more energy, something that can conjure heavy particles out of raw collisions. You need the most powerful machines humanity has ever built. And that is why the hunt now moves to a laboratory beneath the Alps. Beneath the border of France and Switzerland, in a ring 17 miles around, protons race at almost the speed of light and smash together with more energy than anywhere else on the planet. This is CERN, home of the Large Hadron Collider, the machine that found the Higgs particle, and it has a special power that the tritium tanks and short beams do not. It can make heavy things. Every experiment we have followed so far shared a limitation. They were tuned for a lightweight sterile neutrino, a particle barely heavier than the ordinary ones. A tritium decay releases only a little energy, so it can only make particles up to a certain small weight. A reactor's antineutrinos are gentle. These machines could probe the featherweight end of the sterile family, and they did, and they mostly came up empty. But the heavier versions of the sterile neutrino, the ones that could be dark matter or the seed of all matter, weigh far more. To create a particle, you need to pour in at least as much energy as its mass demands. Making a heavy, sterile neutrino requires a colossal concentration of energy, focused into a tiny point for the briefest instant. That is precisely what a great collider does. There is a name for this heavier ghost. Physicists often call it a heavy neutral lepton, to distinguish it from the featherweight sterile neutrino of the anomalies. Same basic idea, a neutrino-like particle that shuns the ordinary forces but with a substantial mass, somewhere from a fraction of a proton's weight up to several times a proton's weight. This is the sweet spot that the seesaw and leptogenesis both like, and it is a range that a machine at CERN can reach. So the hunt changes character completely. At CERN, you would not catch the heavy neutral lepton by watching ordinary neutrinos disappear. You would try to make it directly, to conjure it into existence out of a collision, and then catch it in the act of falling apart. Because a heavy neutral lepton, unlike its featherweight cousin, would be unstable. Create one, and it would live for a short while, then decay into ordinary particles you can see and measure. Catch that decay, reconstruct the particles flying out of it, and you would have caught the ghost through its brief, blazing life and death, not merely a shadow it left behind. This is a fundamentally more powerful way to hunt. A footprint can be faked, but if you actually produce the particle and watch it decay into a specific, reconstructible set of debris, that is a capture, not a hint. It is the difference between finding paw prints in the mud and holding the animal in your hands. CERN turns out to be almost perfectly suited to this. Its collisions produce neutrinos of every kind in enormous numbers, and its beams of protons can be aimed at dense targets to make even more. If heavy neutral leptons exist in the reachable range, CERN has the raw power to make them and the precision to catch them. For a long time, the collider was busy with other prey, chasing the Higgs and its secrets. But recently, almost as an afterthought, physicists realized that the machine had been making neutrinos all along, floods of them, at energies never before seen from any machine, and nobody had ever caught one. So they built small, clever detectors, tucked them into service tunnels far from the main action, and waited for the highest energy artificial neutrinos ever made to arrive. For decades, there was a strange gap in the story of the neutrino. We had caught these ghosts from the sun, from the sky, from reactors, from radioactive sources, even from an exploding star 160,000 light-years away, from nearly every source in nature. But there was one obvious source we had never caught a neutrino from: a particle collider. This was almost embarrassing. Colliders like the one at CERN produce neutrinos in staggering numbers every time they run. When protons smash together, the debris includes torrents of neutrinos of all three flavors, flung forward along the beamline. They had been pouring out of every collision for years, and not once had anyone directly detected one, because the giant detectors at the collision points were built to catch other things, and the neutrinos sailed straight through them and away. The neutrinos from a collider are special in one thrilling way. They are the most energetic neutrinos ever produced by human hands, far more energetic than those from reactors or ordinary beams. At these enormous energies, neutrinos interact a little more willingly, which means, for once, they are slightly easier to catch, and their behavior at such energies had never been tested. There could be surprises hiding there, cracks in the standard model, hints of new physics, waiting in a corner nobody had ever looked, so 2 small experiments were built to catch them. One was tucked into an old service tunnel, a passage that once linked older machines, sitting about 1/3 of a mile from where the protons collide, directly in the line of fire of the forward neutrino beam. The other sat on the opposite side, a compact detector layered with dense material and sensitive film, waiting for a ghost to strike. In 2023, both announced success. For the first time in history, neutrinos made by a particle collider had been directly detected. One experiment reported over 150 neutrino interactions, with a certainty so high that the chance of it being a fluke was essentially zero, a signal towering 16 standard deviations above the background. In particle physics, 5 is enough to claim a discovery. 16 is a thunderclap. The other experiment caught its own batch of muon neutrino events against a whisper of expected background. 2 independent detectors, on 2 sides of the collision, both nailed it. These were the highest energy neutrinos ever directly detected from any artificial source. A new window had opened. For the first time, physicists could study these ghosts at energies where their weak interactions had never been measured, in a controlled laboratory, with a beam they understood. And this is only the opening act. These first detectors are small, pilot efforts. They prove the concept works. They show that you can sit in the forward beam of a collider and reliably catch its neutrinos. That opens the door to bigger, sharper detectors that could measure all 3 flavors, test the standard model at new extremes, and search for the fingerprints of heavier, stranger particles, including the heavy neutral leptons at the center of our hunt. Catching the ordinary collider neutrinos was the proof that the strategy works. Now the same forward region, the same clever placement, becomes a hunting ground for the forbidden ghost. But detecting neutrinos that were going to sail through anyway is one thing. To hunt a heavy neutral lepton on purpose, physicists needed to understand a strange truth about colliders. The most interesting ghosts all fly in the one direction nobody was watching. Every giant collider detector has a blind spot, and for 50 years nobody minded. When protons collide, most of the interesting, heavy particles fly out sideways, at wide angles from the beam. That is where the big detectors focus all their attention, wrapping the collision point in layers of sensors to catch particles spraying outward. The forward direction, straight along the beam line, was treated as a nuisance. It is where the leftover beam goes, a place of debris and glare, not worth watching. But that overlooked direction turns out to be exactly where the ghosts go. Light, feebly interacting particles, the neutrinos and anything like them, tend to fly forward, hugging the beamline, carrying huge energy in a tight cone. The sideways detectors miss them almost entirely. For decades, Every collision sent a brilliant beam of high-energy neutrinos shooting straight down the tunnel, unwatched, straight past the edge of the main detectors and into the rock. Once physicists realized this, a new strategy took shape. Put a small, cheap, clever detector far downstream, right on the beamline, hundreds of yards past the collision, behind enough rock and concrete to filter out the ordinary spray. The everyday particles get absorbed by all that shielding, but the ghosts, the neutrinos, and any exotic feebly interacting cousins pass through the rock untouched and arrive at your little detector clean. This is the trick behind the first collider neutrino detections, and it does something even more powerful. It creates the perfect place to hunt long-lived exotic particles. Here is the key idea. Suppose a collision produces a heavy neutral lepton, our forbidden ghost. Because it interacts so feebly, it would not decay immediately. It would fly for a while first, coasting through the shielding along with the neutrinos, before finally falling apart into ordinary particles. If your detector sits far enough downstream, that decay could happen right inside it or just in front of it. You would see particles suddenly appear out of empty space, springing from a point where nothing should have been, with no track leading in. That sudden appearance, a spray of particles blooming from nowhere in a region swept clean of everything else, is the unmistakable signature of a long-lived ghost coming apart. Nothing ordinary makes that pattern. It is the smoking gun. This is why the forward region has become one of the hottest frontiers in physics. It is cheap, it is clean, and it is exactly where the shyest particles reveal themselves. A modest detector in the right spot, far down the beam line, can hunt for things the enormous main detectors would never catch, because those particles were always flying the wrong way, into the blind spot nobody watched. The first small detectors proved the neutrinos are there and catchable. The next generation aims to turn that same forward window into a trap for heavy neutral leptons and other hidden particles, watching for the telltale bloom of a decay in an empty room. But the collider's forward beam, for all its power, is a byproduct. The neutrinos and any exotic particles come along for free, in whatever numbers the collisions happen to make. To truly maximize the odds of catching a heavy neutral lepton, physicists wanted something built for that single purpose. A machine that manufactures ghosts by the trillion, on demand, and clears away everything else so the ghost stands alone. That machine has a name, and it was approved to be built at CERN. The strategy sounds almost crude. To hunt the most elusive particle in physics, you take a beam of protons and slam it straight into a solid block of dense metal. No delicate collisions, no careful tuning, just an intense beam and a wall. This is called a beam dump, and it is one of the cleverest ideas in the whole hunt. When a torrent of high-energy protons crashes into a thick, dense target, it produces an enormous spray of particles. Most of them are ordinary and short-lived, but buried in that spray, if nature allows it, would be a rare few heavy neutral leptons, our forbidden ghosts, born in the violence of the impact. The beam dump becomes a factory, churning out vast numbers of particles, and among the flood, a handful of the thing we are actually looking for. The genius is in what comes next. After the target, you place a thick wall of material and a powerful system of magnets. Everything ordinary gets absorbed or swept aside. The common particles slam into the shielding and stop. Charged particles get bent away by the magnets herded out of the path. What remains, sailing calmly through all of it, would be the ghosts. The feebly interacting particles that ignore the shielding and the magnets alike, precisely because they refuse to interact. Beyond the wall and the magnets, you build a long, empty chamber under vacuum, a stretch of nothing tens of yards long. This is the decay volume. The heavy neutral lepton, having passed through everything else, would fly into this empty space and, at some point along its journey, fall apart into ordinary particles. And because the chamber has been swept clean of everything else, that decay would stand out with perfect clarity, particles blooming out of emptiness where nothing else could be. Think about the elegance of it. You make ghosts by the trillion in a violent impact. You use walls and magnets to strip away every ordinary thing, and you leave a long, empty, watched corridor where the only thing that can possibly show up is the decay of a particle that ignored all your shielding. If a spray of particles appears in that corridor, springing from a single point in the vacuum, it can only be a ghost coming apart. There is almost nothing else it could be. This is the opposite philosophy from the giant collider detectors, which drown in a fire hose of collisions and must sift the interesting events from a mountain of noise. A beam dump aims for silence. It wants a nearly empty stage, so that when the rare ghost finally appears, there is no crowd to hide it. The beam dump approach also reaches exactly the mass range that matters most. It is tuned for particles from a fraction of a proton's weight up to several times a proton's weight, the sweet spot the seesaw and leptogenesists prefer, the range where the heavy neutral lepton could explain neutrino mass and the origin of matter. It reaches couplings so feeble that the particle could have slipped past every previous search. A light thing that stays hidden simply because it barely interacts at all. CERN already has the perfect beam for this, an intense stream of protons from a machine that feeds the Great Collider. And in 2024, after years of proposals and studies, a new experiment built entirely around this strategy was approved. Its name states its mission plainly. It is called the Search for Hidden Particles. The experiment is called SHIP, short for the Search for Hidden Particles, and it represents a decisive bet by CERN. For years, the world's biggest collider chased heavy particles by cranking up the energy, expecting new physics to appear as ever more massive things. It mostly did not. The Higgs was found, and beyond it, a frustrating silence. No new heavy particles leapt out of the highest energy collisions. That silence sent physicists a message. Maybe the new particles are not too heavy to find. Maybe they are light, but so feebly interacting that they have slipped through every net. Maybe we have been searching along the wrong frontier all along, pushing for more energy when we should have been chasing fainter and fainter interactions. SHIP is built for that other frontier, the frontier of feebleness. First proposed over a decade ago and approved in 2024, it will be built in an existing experimental hall at CERN, fed by an intense beam of protons that no other experiment was using. It is designed to hunt the whole family of hidden particles, and the heavy neutral lepton, our sterile neutrino grown massive, sits near the top of its list. Over roughly 15 years of operation, SHIP will send an almost unimaginable number of protons into its target. The figure is written as a 6 followed by 20 zeros, a number so large it defies any everyday comparison. Each of those protons is a chance to make a ghost. With that many attempts, even a particle that is created only once in a trillion collisions would show up, again and again, in the clean corridor beyond the wall. This is the key to hunting something so feeble. If a particle interacts a trillion times more weakly than an ordinary neutrino, you simply make a trillion times more chances for it to appear. Brute quantity overcomes extreme shyness. SHIP is designed to produce more of these hidden particles than any experiment before it, and to do so in an environment swept almost perfectly clean. Its reach is what makes physicists genuinely excited. Across a wide band of the heavy neutral lepton's possible masses and couplings, SHIP would probe territory that no existing or planned experiment can touch, reaching sensitivities far beyond anything achieved so far. If a heavy neutral lepton exists anywhere in that vast, unexplored range, in the sweet spot the theory loves, SHIP has a real chance of catching it, and if it catches even one, the consequences would be staggering. A single confirmed heavy neutral lepton would be the first particle ever found that lives outside the standard model. It would be direct proof that the great theory is incomplete, that there is a whole hidden sector of reality we have only just begun to see. It could be the particle that gives ordinary neutrinos their featherweight mass. It could be the dark matter that binds the galaxies. It could be the very thing whose lopsided decay in the first instant let matter win its war against antimatter and let a universe of stars and planets and people exist at all. SHIP will not begin its hunt for a few years yet. The facility must be built, the detectors assembled, the beam prepared. It is scheduled to start peering into its clean corridor in the early 2030s. And SHIP is not the only weapon CERN is bringing to this fight. Another experiment, already running, hunts the same ghost inside the death of a much smaller particle. Not every hunt for the heavy neutral lepton needs a giant beam dump. Some of CERN's best hunting happens inside the death of a single, humble particle called the kaon. A kaon is a small, unstable particle, made and studied by the millions at CERN. Left alone, a kaon falls apart in a fraction of a second, decaying into lighter particles. Physicists have studied these decays for decades, cataloguing every way a kaon can die and how often each way happens. And that catalogue is a hunting ground. Here is the idea. When a kaon decays, it releases a certain amount of energy, shared among the particles it produces. If a heavy neutral lepton exists and is light enough, then very rarely a kaon could decay into it, along with an ordinary partner particle. The ghost would be one of the products of the kaon's death. The experiment that hunts this way is called NA62, and it was built to study the rarest kaon decays with extraordinary precision. It watches enormous numbers of kaons fall apart, measuring every decay with such care that it can spot the faint signature of a heavy neutral lepton hiding among them. If the ghost is produced, it would show up as a tiny bump, a slight excess of decays with a particular energy, at a spot in the data where the mass of the hidden particle reveals itself. This gives CERN a second, completely different way to hunt the same forbidden particle. The beam dump makes ghosts in the raw violence of protons hitting a wall. The kaon experiment catches them in the delicate, precise decay of a single small particle. 2 methods, 2 mass ranges, 2 chances to catch the same prey. If one misses, the other might succeed. There is something poetic about this approach. The kaon is itself a particle that helped teach us about the deep asymmetries of nature, the tiny imbalances between matter and antimatter that hint at why the universe survived. And now, in its everyday decays, it might reveal the very particle theorists believe could explain that survival. The heavy neutral lepton could be hiding. Right now, in a fraction of the kaon decays, physicists have been watching for years, waiting to be noticed. NA62 has already set limits, searching through its mountain of kaon decays, and so far, finding no clear sign of the ghost. But each new batch of data pushes the search deeper, closing off more of the range where the particle could hide, or, one day, revealing the faint bump that would announce its presence. Between the beam dump and the kaon hunt, CERN is coming at the heavy neutral lepton from multiple angles at once, covering different masses, different couplings, different corners of the vast space where the ghost could live. This is how you corner something that has evaded capture for so long. You do not rely on a single trap. You surround it, and CERN is not hunting alone. On the other side of the Atlantic, at Fermilab, an entire program of experiments has been built around the sterile neutrino question, using the same liquid argon technology that let Microbuni deliver its verdict. Where Microbuni looked for the ghost one way, its siblings look for it in others, watching the same beam with different detectors at different distances, determined to leave the featherweight sterile neutrino nowhere to hide. Their combined verdict would either bury the light ghost for good or force physics to admit that something in that beam still cannot be explained. At Fermilab, near Chicago, physicists built something they called a short baseline program, a set of liquid argon detectors placed along a single neutrino beam at different distances, designed to gang up on the sterile neutrino from every angle at once. Microbuna was the middle child of this family, but it has siblings, and one of them is a giant with a remarkable history. That detector is called Icarus, and it is a veteran. It was first built and run years ago under a mountain in Italy, one of the pioneers of the liquid argon technique, proving that you really could photograph the tracks of particles in a cold, clear pool of argon. Then, in an extraordinary journey, the massive detector was shipped across the ocean to Fermilab, refurbished, and installed in the neutrino beam to join the hunt. A machine built in Europe now stands in Illinois, searching for the same ghost from a new position. The power of placing detectors at different distances along one beam is that it isolates oscillation. Neutrinos change flavor as they travel, so the pattern of what you see depends on how far the beam has gone. A detector close to the source sees the beam almost fresh, before much oscillation has happened. A detector farther away sees the beam after it has had time to change. Compare the two, and any funny business, any disappearance or appearance that the three-flavor picture cannot explain jumps out clearly. A sterile neutrino, stealing neutrinos out of the beam at a certain distance, would reveal itself in the difference between the near and far detectors. Icarus went looking for exactly that. It watched muon neutrinos in the beam and asked whether any of them were vanishing at short range, disappearing into the sterile state as a heavier ghost would cause. This is the disappearance signature, the quiet theft of neutrinos, the other side of the coin from the electron appearance that Minibuni saw. And Icarus, in its first oscillation results, found no significant disappearance. The muon neutrinos arrived in the numbers the ordinary picture predicted. No sign of a sterile neutrino, stealing them away at the baseline it watched. Another careful look, another empty net for the featherweight ghost. Piece by piece, the Fermilab program and the German tank and the CERN searches are painting the same picture for the light sterile neutrino. The simplest version, the one tied to the classic anomalies, keeps failing to appear wherever a sharp enough experiment looks for it. Its territory shrinks with every result, and yet, remember the strangeness at the heart of this. Even as the simple ghost fades, the original anomaly that started it all, the excess Minibuni saw, remains real and unexplained. Ruling out the sterile neutrino did not make the mystery vanish. It only made it deeper and stranger by taking away the answer everyone had counted on. So the field stands at a genuine crossroads. The featherweight sterile neutrino is nearly cornered. The heavier versions, the ones CERN's beam dump and kaon hunts are built to chase, are wide open and untested, and the anomalies still whisper that something, somewhere, is not accounted for. To settle it, physicists are also building the most precise neutrino observatories ever made, machines that will measure the ordinary 3 neutrinos so exactly that any hidden fourth would have nowhere left to lurk. And the first of these giants just switched on, deep underground in southern China. In a cavern carved deep beneath a hill in southern China sits a sphere so large it strains belief. It is filled with 20,000 tons of a special clear liquid that flashes with light whenever a neutrino interacts within it, and it is watched by tens of thousands of light sensors, staring inward from all around, like a great eye lined with smaller eyes. It is called Juno, and it began its hunt in the late summer of 2025. Juno is not primarily a sterile neutrino experiment. Its main mission is even more fundamental. It aims to measure the ordinary 3 neutrinos with a precision no machine has ever achieved, to nail down the exact way they oscillate, and, above all, to settle a stubborn open question about which of the 3 neutrinos is heaviest and which is lightest. This is called the mass ordering, and it is one of the last great unknowns of ordinary neutrino physics. Why does this matter for the ghost? Because precision is a weapon. The better we understand the ordinary 3-flavor picture, the more clearly any deviation from it stands out. A sterile neutrino, if it exists, distorts the pattern of oscillation. It bends the curves, shifts the numbers, leaves subtle fingerprints on how the ordinary neutrinos behave. But you can only see those fingerprints if you know exactly what the ordinary behavior should look like. Juno's extraordinary precision turns it into a detector of the three known neutrinos and of anything that disturbs them. Juno watches antineutrinos streaming from distant nuclear power plants, tens of miles away, catching them after they have traveled just the right distance to reveal their oscillation in fine detail. From the exact shape of what it sees, it can extract the properties of the neutrinos with unprecedented sharpness. And woven into that same data is the power to test for a sterile neutrino, to check whether the ordinary three tell a complete story or whether a hidden fourth is subtly pulling the strings. Juno is the first of a new generation of enormous, precise neutrino observatories now coming online. Together, these machines will measure the ghosts we already know with a care that would have seemed impossible a generation ago, and either confirm that three flavors explain everything or expose the faint distortions that betray a fourth. There is something fitting about this. The sterile neutrino hunt began with imprecision, with small anomalies at the ragged edge of what old detectors could measure. The way to finally resolve it is with the opposite, with overwhelming precision, machines so exact that a real deviation could no longer hide behind uncertainty, and a false one could no longer masquerade as a discovery. Juno switching on marks a turning point. The era of ambiguous hints is giving way to an era of decisive measurement. The ghost will no longer be able to lurk in the fog of imprecise data. It will either show itself clearly or be ruled out cleanly, across range after range. But no single experiment, however grand, can search the whole vast space where the sterile neutrino might live. The featherweight version, the dark matter version, the heavy version tied to the origin of matter, each hides in a different range. Each demands a different kind of machine. To catch a ghost that could weigh almost anything, the hunters realized they would have to work together and coordinate their traps across the entire globe. At CERN, in the autumn of 2025, they began to do exactly that. In October of 2025, about 100 physicists gathered at CERN for the kickoff of a new collaboration with an unusual goal. It was not built around a single detector or a single beam. It was built to tie the world's neutrino experiments together into one coordinated hunt. The effort is part of a wider push to make sure the many powerful neutrino experiments now being built do not simply work in isolation, each looking at its own small patch, but instead complement one another, covering the whole vast landscape where hidden physics might live. Different experiments watch different distances, different energies, different flavors, different mass ranges. Alone, each is a single searchlight sweeping one corner of a dark field. Together, coordinated, they can illuminate the entire field at once. This is the shape the hunt has taken as it matures. In the early days, one lonely experiment would see an anomaly, and the world would argue about it for years, unable to confirm or kill it because no other machine was aimed at the same target. That is how the desert anomaly hung unresolved for so long. That is how the reactor and gallium puzzles lingered. The lesson, learned the hard way, is that you cannot corner an elusive particle with scattered, uncoordinated efforts. You need overlap. You need many machines whose ranges cross, so that a real signal must show up in more than one, and a false one gets exposed by the disagreement. So the field is organizing itself into a global campaign. The giant precision observatories will pin down the ordinary neutrinos. The liquid argon detectors at Fermilab will hunt the featherweight sterile neutrino from every angle along a single beam. CERN's beam dump and kaon experiments will chase the heavier ghost, the massive hidden lepton, into ranges no one has ever explored. Telescopes in space will scan the heavens for the faint glow of a decaying dark matter neutrino, and a new coordinating effort will help stitch these searches into a single, comprehensive net. The reason for all this effort circles back to the stakes. The sterile neutrino, in one form or another, touches nearly every deep mystery physics has left unsolved. Its featherweight version might explain the strange anomalies that have haunted the field for 30 years. A middleweight version could be the dark matter that outweighs every star. A heavier version could be why ordinary neutrinos weigh almost nothing, and why matter survived the annihilation that should have left the universe empty. No single idea in modern physics reaches into so many unsolved problems at once. And that is precisely why the hunt cannot be abandoned, even as the simplest version keeps failing to appear. Each empty result does not close the case. It narrows it. It tells the hunters where the ghost is not, and points them toward the ranges where it still might be. The featherweight end is nearly ruled out. The heavier ranges remain wide open. The dark matter range is only beginning to be searched. To reach that dark matter range, the one where a sterile neutrino could be the invisible substance holding the galaxies together, physicists needed to extend their most sensitive weighing machine into new territory. And the great steel tank in Germany, the one that already came up empty in the featherweight search, was about to be upgraded to hunt exactly there. The great steel tank in Germany had searched the featherweight range and found nothing, but its designers always knew it could be pushed further, and in 2026, it is being transformed to hunt a heavier, far more exciting prey, the sterile neutrino that could be dark matter. The upgrade is called Tristan, and it changes what the experiment can see. The original setup measured only the very tip of the electron energy spectrum from decaying tritium, the small region where the featherweight neutrino's mass leaves its mark. The upgrade installs a new detector able to read the entire spectrum, the whole broad sweep of electron energies, far beyond the narrow tip. Why does this open a new window? Because a heavier sterile neutrino leaves its kink deep in the body of the spectrum, far from the very tip, at a place set by its larger mass. To catch a much heavier ghost, you have to measure electrons across the full range, watching for a step buried far from the edge. The original detector could not do this. The upgraded one can. It extends the search from the featherweight range up into the range where a sterile neutrino could weigh thousands of times more, right into the sweet spot for dark matter. This is thrilling because it means the same beautiful, clean method that ruled out the featherweight ghost can now be turned on the dark matter candidate. No murky reactor predictions. No electron versus photon confusion. Just an unimaginably careful measurement of electron energies, now sweeping across the whole spectrum, hunting for the faint kink that a dark matter sterile neutrino would carve into it. If it finds that kink, the consequences would be almost beyond words. It would mean the invisible substance holding the galaxies together, the dark matter that makes up most of the matter in the universe, is a sterile neutrino, a heavy cousin of the ghosts already pouring through your body. The mystery that has baffled astronomers for nearly a century, the unseen mass gripping the stars, would suddenly have a name and a face, and it would be a particle from outside the standard model, proof that our deepest theory is only part of the story. The hunt for the dark matter sterile neutrino is happening on two fronts at once, and they check each other beautifully. In the laboratory, the upgraded tank searches for the kink in the electron spectrum, trying to catch the particle in the decay of an atom. In the sky, X-ray telescopes scan galaxies and clusters for the faint glow of these same particles slowly decaying, releasing their telltale flash of light at one exact energy. If both the laboratory and the heavens pointed to a sterile neutrino of the very same mass, the case would be overwhelming. A particle found in a German tank and in the light of distant galaxies, matching perfectly, would be one of the greatest discoveries in the history of science. And there is a third front, stranger than the others, where the ghost may already be leaving a trace. The universe itself, in its largest structures, keeps its own record of how many neutrino-like particles have ever existed. When astronomers read that record, using maps of millions of galaxies and the faint afterglow of the Big Bang, they sometimes find a whisper of an anomaly, a hint that the number does not quite match the ordinary three. The entire cosmos, it turns out, may be the largest ghost detector ever built. The universe keeps books. Everything that existed in its first hot moments left a mark on how it grew, and by reading that mark, Physicists can count particles that vanished billions of years ago. Here is the astonishing part. If there was a fourth neutrino-like particle in the early universe, even a sterile one, it would have added to the total soup of radiation filling all of space. That extra particle would have changed how fast the universe expanded and how matter clumped into the first galaxies. Its presence, or its absence, is written into the large-scale structure of the cosmos, in the way galaxies are scattered across the sky and in the faint afterglow left over from the Big Bang. So astronomers have learned to weigh the early universe's particle content by studying maps of the cosmos. They chart the positions of millions of galaxies, measuring the subtle patterns in how they cluster. They study the ancient light released when the universe first became transparent, reading tiny variations in its temperature. From these grand cosmic surveys, they can estimate how many kinds of light, fast-moving particle were present in the early universe, and roughly how much they weighed. For a long time, these cosmic measurements were bad news for the sterile neutrino. A featherweight sterile neutrino of the kind the anomalies suggested would have been produced in abundance in the early universe, and its extra mass and radiation would have left marks that astronomers simply did not see. The cosmos seemed to say, firmly, that there was no room for an extra neutrino of that weight. This tension between the laboratory hints and the cosmic surveys was one of the strongest arguments against the featherweight ghost all along. But the story has a recent twist. A vast new survey, mapping the positions of millions of galaxies to trace the structure of the universe with unprecedented reach, has been refining these measurements. And in certain analyses, combining this new galaxy map with the ancient afterglow and other cosmic data, a faint hint has emerged. Under some assumptions, the data seem to prefer a small but non-zero mass for an extra sterile neutrino, at a modest level of confidence, too weak to claim anything, yet enough to make physicists look twice. It is a whisper, nothing more. Cosmic measurements are subtle and depend on assumptions about how the universe has evolved, and different assumptions give different answers. No one is announcing a discovery from the sky, but it is a reminder that the cosmos itself is a detector, perhaps the largest one of all, and that it has not entirely closed the door on the ghost. So the hunt now spans an incredible range of scales. Tiny tanks of gallium and tritium probe the ghost through single atoms. Beam dumps and colliders try to conjure it from raw energy. Precision observatories watch the ordinary neutrinos for its fingerprints. X-ray telescopes scan the galaxies for its dying glow, and the entire universe, mapped across billions of light years, keeps a faint tally of how many such particles have ever been. From the smallest atom to the largest structure in the cosmos, every scale of reality is being searched for the same forbidden particle, which brings us to the question that hangs over all of it. After 30 years of hints and heartbreaks, of anomalies that flare and fade, of empty nets and stubborn mysteries, what happens if they actually find it? What would it mean to hold, at last, a particle from outside the rules? Imagine the day, in a clean corridor beyond a wall of metal at CERN, or in the electron energies of a decaying atom in Germany, or in the light of a distant galaxy, a signal appears that cannot be explained any other way. A spray of particles blooming from empty space, a kink in a spectrum, a glow at one exact color, and after every check, every doubt, every effort to explain it away, it holds. A sterile neutrino, a particle from outside the standard model, confirmed. It would be one of the largest discoveries in the history of physics. Consider what a single such particle would settle. For 60 years, the standard model has reigned as our deepest description of reality, and for 60 years, it has been almost frustratingly perfect, passing every test, refusing to crack in any clear way. Physicists know it must be incomplete, because it cannot explain neutrino mass, or dark matter, or why matter survived the Big Bang. But it has stubbornly refused to show them the door to what lies beyond. A confirmed sterile neutrino would be that door, flung open. The first particle ever found that the theory did not contain direct, undeniable proof that there is more. And it would be far more than a new particle. It would be a key that unlocks several locked rooms at once. If the sterile neutrino explains why ordinary neutrinos are so absurdly light, then finding it would solve a mystery that has stood since we first learned neutrinos have mass at all. If it turns out to be the dark matter, then finding it would name the invisible substance that makes up most of the matter in the universe and holds every galaxy together, ending a hunt that has consumed astronomy for nearly a century. And if it is the particle whose lopsided decay in the first instant of time tipped the balance toward matter, then finding it would answer the oldest question of all: why is there something rather than nothing? One particle, three of the deepest mysteries in science. That is the prize that keeps the hunters going, through empty result after empty result. That is why they build tanks the size of blimps and corridors swept clean under vacuum. If it is real, it changes everything. There is even a chance the discovery would go further than anyone expects. A truly sterile particle is a doorway to what physicists call the hidden sector, a whole possible family of particles that shun the ordinary forces and interact with our world only faintly through the narrowest of channels. The sterile neutrino might be the first of many. Finding it could be like finding the first crack of light under a door behind which an entire unseen half of physics is waiting. We might discover that the visible universe, everything we have ever studied, is only one room in a much larger house. This is the dream that pulls physicists to work every morning, to find the particle that the rules forbid, to prove that reality is bigger than our best theory, to reach through a hidden door and pull out something that rewrites the textbooks. But there is another possible ending to this story, and it is almost as profound. The hunters might search every range, with every machine, across every scale from the atom to the cosmos, and find nothing at all. And that outcome, the empty universe, the ghost that was never there, would carry a strange and heavy lesson of its own. There is a real possibility, growing more real with each empty result, that the sterile neutrino does not exist, that the anomalies were a long chain of coincidences and mistakes, that the beautiful theories which summoned the ghost, the seesaw, the dark matter, the origin of matter, are true in some form that keeps the hidden particle forever out of reach, or are simply wrong, that physics chased a phantom for a generation and, in the end, came home empty-handed. If that is the answer, it would be a disappointment. But it would also be a triumph of a quieter kind. Think about what the search has already accomplished. In hunting a particle that may not exist, physicists have measured the ordinary neutrinos with staggering new precision. They have built detectors that photograph the path of every particle in cold, clear argon. They have caught the highest energy artificial neutrinos ever made, in tunnels no one thought to watch. They have learned to weigh a single decaying atom with almost impossible care, and to read the particle content of the early universe from maps of distant galaxies. The tools built to catch the ghost have opened whole new windows on reality, whether or not the ghost was ever there to catch. And ruling something out, cleanly and completely, is a kind of knowledge, not a failure. Every range the hunters close off, every mass they eliminate, sharpens the picture of what the universe actually contains. When the two great experiments came back empty in the same season, they did not waste those years. They told us, with new certainty, where the answer to the anomalies does not lie. That forces physics to look elsewhere, to invent new ideas, to confront the mysteries that remain without the comfortable crutch of the sterile neutrino to lean on. Because those mysteries do not go away. That is the crucial point. Even if every sterile neutrino search fails, ordinary neutrinos still have mass that the standard model cannot explain. Dark matter still grips the galaxies. Matter still, impossibly, won its war against antimatter. The questions that conjured the ghost are still standing, still demanding answers. If the sterile neutrino is not the answer, then something else, something we have not yet imagined, must be. And that unknown something would be even stranger than the ghost we chased. So either way, the hunt reshapes physics. Find the sterile neutrino, and we hold the first particle from beyond the rules, a key to three of the deepest mysteries at once, a crack of light under the door to a hidden half of the universe. Fail to find it, and we are forced back to the drawing board on the greatest questions in science, armed with sharper tools and a clearer map of the dark. The ghost may be real. The ghost may be a mirage. Right now, tonight, in a laboratory beneath the Alps and in tanks and tunnels and telescopes around the world, the smartest people alive are building the machines that will decide. They are hunting a particle that touches nothing, that hides from every force, that the rules of physics say should not be there. And whether they catch it or prove it was never there, the answer will tell us something we do not yet know about why the universe exists and what it is truly made of. The hunt is far from over. Somewhere in the space between the smallest atom and the largest galaxy, an answer is waiting.